So the last type of function that we haven't really seen how to take the derivative of is the inverse function. So it's not really a type of function. It's more like a general class on its own, right? So just a little bit of a reminder of what an inverse function is real quick, right? If we have like f of x equals x plus 3, the inverse function, f inverse of x, is the function which does the opposite thing, right? So like in this case, it would be x minus 3. So in general, two functions are inverses of each other if f of f inverse of x equals x and f inverse of x of f of x equals x. Okay, so they're inverses in the sense of function composition. So what if we want to take the derivative of an inverse function? Okay, so we could just find the inverse and then we could take the derivative of it, right? That's always a possibility. But maybe we don't actually know what the function is, or maybe it's hard to find the inverse of it. So maybe we want an alternative way. So first, a little bit about the notation here that can get a little bit confusing. When we are using the inverse notation and the derivative notation, right, specifically the prime notation, we want to differentiate between f inverse prime of x and f prime inverse of x, right? So these are a little bit different. The first one is the derivative of the inverse of f. The second one is the inverse of the derivative of f. Okay, so these are naturally going to be different things, right? So for example, if we have f of x equals x cubed, which would mean that f inverse of x equals the cube root of x, okay, then f inverse prime of x, the first one over here, would be f inverse prime of x would be the derivative of the cube root function, which would be 1 over 3 x to the 2/3, right? Whereas the inverse of f prime would be the inverse of 3x squared, which would be it's a little bit harder to say here because x squared doesn't necessarily have an inverse unless we cut off the domain from at 0, which we definitely can do. So I guess we could say that it's the square root of x over 3, right? All under the square root, to be clear. So yeah, so this is what would be what it would end up being, I think. Okay, again with the caveat that you're cutting off the domain at a certain point. But anyway, the big point is that these are very different things, right? So it's easy to get them confused because the notation is kind of similar, right? Using the 1 and the prime, they kind of blend together. So we just want to be very careful about what exactly it's saying. So the first one's saying take the derivative of the inverse function, and the second one is saying take the inverse of the derivative function. Okay. So anyway, with that out of the way, let's go ahead and look at, okay, how do we actually take the derivative of the inverse function? And we can get it from that identity that I wrote up above, namely that f of f inverse of x equals x. Okay, so with this, we can take the derivative of both sides. Okay, so if we take d dx of both sides. Okay. Then what happens is on the right side we get d dx, right? So I'll just or I'm sorry, actually we get 1, right? So I'll just write that on this side, I guess. And then on the inside here, we're using the chain rule, right? So we get f prime of f inverse of x times f inverse prime of x, right? So the derivative of the outside and then the derivative of the inside, which is the inverse function. We're looking for a formula for this, f inverse prime of x. So let's go ahead and bring all the rest of it to the other side, divide it on both sides, and we're going to get f inverse prime of x equals 1 over f prime f inverse of x. Okay. So this is our formula for the derivative of the inverse function. So if we look at the one we just did, right, we just found the derivative of f prime inverse of x up here, right? So we had the f of x equals x cubed, and then f inverse of x equals the cube root of x. So the derivative, we got 1 over 3 times x to the 2/3. So let's make sure we get the same thing with this new formula. Okay. So we would need f prime, and then we need to put f inverse into it, right? So again, f of x equals x cubed here on this example. So let me change the color here to distinguish that this is an example. Okay, so f of x equals x cubed. So we already established f inverse of x is equal to cube root of x. Okay, so now we would see that f inverse prime of x, trying to be very careful about writing it properly. Again, we also need f prime of x, so this is going to be 3x squared. So this is going to be equal to 3x squared with the cube root of x put into it, right? So we compose the f prime of x with the inverse function, cube root of x. So 3 cube root of x squared, which is indeed the same thing as 3 times x to the 2/3. Okay, which is what we just got right here as well, using the power rule. Okay, so in a lot of cases, you might not need this formula necessarily because you can just find the inverse function and then take the derivative of it. In fact, for this, you need that inverse function. So this is most helpful, I think, when you're trying to do this at a single point, right? Sometimes problems will ask you to find the value of this, like maybe at like 2, for example, and they won't actually give you the function, right? So then you'll need this formula to know exactly what the derivative at this point is. This is also gives us an alternate way of proving that the derivative of the natural log function is 1 over x. I don't think that we actually did a proof of it. I could be wrong, but if we let f of x equal e to the x, okay, then f inverse of x is the natural log of x. Okay, and then the f prime of x is also e to the x. And now that I think about it, I think we did do the proof of it but we used implicit differentiation and we hadn't gotten there yet. So it's always good to go back and look at it now that we did do implicit differentiation, by the way. So now we can use our formula here. So we'll do 1 over f prime of f inverse of x. So this is going to be 1 over e to the natural log of x, right? Because we're composing these functions. So we're putting the inverse function into the derivative function. And e to the natural log of x is just x. So this is 1 over x. Okay. So a more natural proof of, or not more natural, but just an alternative proof that doesn't rely on the implicit differentiation. Okay. And you could do the same thing with natural log of x. Like you could start with natural log of x and then prove the derivative of e to the x is e to the x, right? So you could do this with any of the inverse functions, of course. If you look at trig a little bit more, you can also then use this to show that the derivative of arctan, where arctan is the inverse function of tangent, is equal to 1 over 1 plus x squared. Okay, so arctan of x is equal to the inverse function of tanvis. So we tangent. So we like to use arctan instead because tangent of -1, it's kind of ambiguous whether that means arctan or cotangent, that are reciprocal. So we prefer to use arctan, but if you look on your calculator, it probably says like tangent inverse, right? So again, you can use this formula to do that. You need a little bit of trig and geometry in there, so I'll skip the derivation of it because, like I've been saying, we're not going to do a lot of trig. We don't need it a lot for statistics. So, but I think this is a good one to mention still, and maybe a good one to try out. Just because the derivative of arctan we might not ever need, but when we look at integrals, when we go the other way, this is a kind of a common form that might pop up, and it's good to know that the integral of this would be arctan, meaning the antiderivative.